welcome in. All right, so tension force. Okay, so we're going to make a few assumptions when you're going to be calculating this. So when you're getting into your introductory physics and you start talking about forces, you can make these particular assumptions, and typically they are made by your teachers or your profs or whoever is teaching this. So one of the assumptions is that tensions, typically will be kind of applied through or passed along some kind of a rope or a string. So that is something that we think about. Now, if you have a box, okay, so let's say if it's a box and there's a rope that's attached, and there are no actual forces which are pulled, okay, within here, then this rope is just going to be lying down. There's going to be nothing, okay, that's going to happen to it. But as soon as you kind of pull on it, then what will happen is that you can transfer the force and then it becomes tightened, okay, so depending on how you're pulling this, and then you're going to have a tension force inside there. Now, it is always done through some kind of a pull. So you can't really push on a rope, you can only pull. So that's one thing that we should remember. The other thing is that we should know is that we're going to assume, okay, that these particular ropes or strings are not stretchable, right? So now they are normally stretchable. You can stretch them up to a certain point, but we'll assume in all the calculations that you can't really stretch them, which means that it makes our calculation simple. It just means that they're kind of, infinitely durable and they just stay as fixed as they are. The other concept that you should assume is that the actual tension itself is uniformly spread throughout the rope. So no matter where, okay, if you would put a measuring device on trying to measure what the force is, okay, so everywhere it's going to be uniform. It's going to be constant all the way throughout, okay? So anywhere along, okay, within here, it's going to be the same exact tension. Okay, so now with that in mind, let's take a look and break down how these tension forces work. So like, where do we use them, and some of the concepts or examples that you might run into. So here's a very simple one. So let's say you have some kind of an object and it's suspended, right? So it's being basically suspended. Let's say it's off of a rafter, maybe the wall, okay, the ceiling itself, and it's on some kind of a string or a rope, all right? So we're going to be assuming that this particular object is 5 kilograms in mass. Now, and it's not moving anywhere, so it's basically just suspended. It's almost like you can think of a chandelier. And you would want to be able to figure out, okay, so what tension are we going to have in this string, in this rope, or whatever it is hanging on, a wire possibly, that it has to withhold that 5 kilograms so it doesn't snap on us. So what is that particular tension? So how would we actually measure this out? And this is where you're going to start using basically all of Newton's laws, right? So because this is at rest, so it's not really moving, so that's kind of Newton's first law, right? There are going to be total forces that you have applied, so you can kind of think of F net. So that's something that you have. And then also there's the concept of action and reaction of Newton's third law as well, okay, that is applied. So let's take this and break this down and draw a free body diagram in here. So if I would replicate this, so let's say if this is indeed my object, okay, so I'm going to just replicate it, put it on the side, and I'm going to just change this style, let's say to red for the moment. So what actual forces would I have applied here? Well, I know that I will have the force of gravity, so that's going to be one of the forces that is applied in here. And that force of gravity is always mass, okay, times gravity itself. So I know what exactly this is. This would have been 5, which is the mass, so 5 kilograms multiplied by 9.8, and it's going to give us everything in newtons because it's all nicely consistent. So we have kilograms and then gravity is 9.8, at least approximately meters per second squared. So we have this. Now, if we had nothing else here, then basically this chandelier or this box, whatever is hanging, would just start to fall, right? So this would have been the net force, and it would have just started to come down at 9.8 meters per second squared in terms of its acceleration. But it's at rest. So, so from Newton's law, okay, so that means that the net external force has to be 0. So if the net external force has to be 0, the actual force that's holding it back is going to have to be the force, and this is going to be the force, which is the actual tension force, which is coming in the actual wire or string or rope that we have in there. So now we have those two forces, and if you want to be able to think of what that actual tension is, well, if you have that your net force is indeed equal to 0, so what that means is that your force of gravity, okay, that you have, plus your force, okay, of tension, okay, that you have. Now we have to be careful here because you have to choose a direction. So it just depends what you choose. If you choose up to be positive, then it's going to be, you know, the force, okay, of the tension is going to be first, and then the force of gravity would be negative. If you choose down to be positive, you know, you can reverse it. So that is up to you. So maybe let me kind of stay consistent on up being positive. And in that case, I would have put the tension force, and then this would have been minus the actual force of gravity. So at least this way, it's all consistent. Okay, so this is what I would have. And now, because this is 0, well, you can clearly see that basically the force of tension is identical to the force of gravity, right? So that is what the tension, right, what that wire or rope or string would have to withhold, right? So this is a very simple example of something being suspended, and you can take a look and then see. So the magnitude's the same, just the direction is different, and it's kind of action and reaction, okay? It's almost like sitting in a chair and you're not falling through it. So that's one example, okay, that you can have. Now you can make this more complicated. So what if we had, you know, two objects, and let's say now we have two wires. So you have one wire over here, and then you have another wire over here. So how would you handle this particular situation, and then how would you be finding out these actual tension forces? So of course, let's assume that, you know, these things, so the net force overall is indeed equal to 0. So this thing is not falling off, and it's actually being suspended. So maybe it's like have a double, some fancy chandelier or something of that nature. All right, so what happens? You know, how do we tackle a question like this? So one of the things that you can do, okay, within here, so I typically would start, and what I'm going to start with is I'm going to group this right here all into kind of one item. So it's almost like I am forgetting that it is two items. I'm going to be kind of shifting this over. That it's basically one item. So it's the 5 kilogram and the 15 kilogram. Okay, so these boxes or chandeliers or whatever it might be. So I'm going to treat them as one. And you might say, well, what about this actual rope? Well, this is where we assume that it kind of doesn't have any mass itself. And actually, maybe that's something that I should have, okay, mentioned within here. So one of the items in terms of the rope and string, yes, we will assume that typically they don't carry a mass, right? So they're kind of just items, although they certainly do have a mass of some kind, but it's negligible. So if this indeed is negligible, right, so this particular rope, so it's almost like these two pieces are attached together, and now they're being just suspended, okay, over this particular whatever string or wire this would be. So how you would handle this is you would say this. You would just say, okay, so my free body diagram now is a combination. Now it will have a force of gravity, which is going to be pulling it down. And this force of gravity now all of a sudden, so its mass is going to be both. So it's going to be the 5 kilograms plus the 15 kilograms that I have. And then it's going to be multiplied by our standard 9.8 meters per second squared. So it's the actual weight. And what happens is, since we do have a net force of 0, so we're at rest, really, this isn't moving, okay, on us. So because of that, that means that the actual tension force, so that tension number 1, so this force of tension 1, has to be equal, basically, to this force of gravity, which is going to be 20 kilograms times 9.8. So that's what it would be. Right? So this is exactly what we would have. So we can certainly calculate that out. So that would have been force, okay, T1. Now we know that it is going to be upwards with regards to that. And so for that, you know, so we can just say 20 multiplied by 9.8, and it's going to be 196. So 196, and, you know, if we were rounding, we can certainly round it if we wanted to. Now this is going to be up. Now, the other item that I didn't mention, okay, is with regards to, and I should have maybe mentioned it in the previous example. So if I come back over here, now this force of tension, okay, is in this direction. So that's over here. Now you might say, okay, well, this is carried through all the way, and that is true indeed. Now this force of tension, okay, if we were doing the actual free body diagram at that point, then what you would have is the force of tension would have been in the opposite direction. So this would have been down, right, because it's being suspended. So this is pulling it down, okay, and the actual, ceiling that you have, okay, is ensuring that it doesn't get dislocated in some way, right? So that there's a both action and reaction force as well, and those two, this force of tension and the actual reaction force, so this is the action force right there, so this is the reaction force right there, okay, so they're kind of balancing each other off as well. So that's what you would have, and this is the same thing that happens at this point. So whatever this is going through, okay, well, this is in the opposite direction that you have in there. So we have 196 newtons, all right, so this is up, okay, based on this free body diagram that we have done. So that means this is 196 newtons down over here. So that's the tension that we would have in this particular rope or string. And now if we wanted to find out what the tension is over here, well, we don't need to actually take into account everything, right? In this case, we would only take into account this particular item. So we would have just simply this. Now this is now 15 kilograms right there. And now this tension force, okay, that we would have, so this one right there, would balance off with this. Now this force of gravity that we have in here is going to be different. So this is 15 kilograms, no longer 20, right? Because we're not considering the actual upper box as well. So it's going to be 15 times 9.8, and then we can get exactly what our answer is in here. And that will balance off because this, the net force for this, is also zero, right? This isn't moving anywhere. And that particular tension gets spread out all the way through here, so uniformly, so it's carried out in here. So at this point, right, so this suspension, so this has to be locked in so that it has to withstand the actual tension that gets pulled through that rope while it is actually withholding that second box which is hanging down. That's what you have right there, and it is being attached over here, and it is being spread out, okay, and it folds, okay, so that box is actually held in there. So that's how you can find these tensions. So you can individually try to figure out exactly what happens, and you can start breaking this down. And if you start doing, more and more of these, so if you started to hang more boxes, which is always a nice exercise to do, if you hung a third one, what do you do in that situation? Now you should know. You can start from kind of the beginning, and then you can, break it down one by one, and then calculate the tensions individually by creating these free body diagrams, right? And then applying Newton's laws to it, remembering that this is stationary. Now, what happens if it's not stationary, right? So let's say, here's another example. It's the last one that I'll present here with regards to these tensions. So let's imagine that we have, it doesn't matter what this is, okay? I just put 3 boxes in here, they're tied in, and they're tied in. So within here, you can imagine there's a rope. Within here, there is a rope, okay? And then, within here, so sure, maybe there's a rope, and it is being pulled, so there's an applied force, which is in this direction, and it's 105 newtons. And now our question will be this, okay? So we're going to ask a few questions here. My first question is going to be, okay, so what is the acceleration on the entire set, okay, of objects, right? So what's the acceleration as a whole if you have an applied force, okay, and that applied force is 105 newtons that you have throughout? We are going to assume, okay, that our force of friction, so let's say that there is a force of friction, we'll assume that it's 0, okay, or it's negligible enough so that, we can slide along. It's almost like it's some kind of a frictionless surface that we can just slide on. So there aren't any other forces that are applied, right? So within here. So, if we wanted to find our acceleration, how would we tackle this? You would tackle it very similarly to what I have just done in the previous example. So what you would do is you would take these and you would treat them as one object. So you would forget, okay, the masses of the ropes, the A and B rope that we have in there, and you would just treat it as one object. And then you would do your free body diagram on this. So how would this look like? So I'm going to draw a free body diagram, and I'm going to say, okay, well, on this free body diagram, this is going to be a mass of 3 kilograms plus 8 kilograms plus 10 kilograms in total. And so that, I guess, will be 21 kilograms that I would have. So it's almost like I'm treating it as one object entirely. And now I would draw all my forces. So I know that I have a force of 105 newtons in here. I have no friction forces, so I don't have any opposing forces due to motion. There's nothing else, okay, in here, except the fact that I do, maybe I'll put this on the side here, that I do have a force of gravity, okay, of course, right there, which is going to be acting. This is going to be the force of gravity. And then there's going to be a normal force. So this normal force, okay, that you have, because of the fact that this entire set of objects, these 3 objects, they're just moving to the right, okay, we'll assume right is positive in here. If we're assuming that they're moving to the right, these particular objects are not going up or down. So that means that this force of gravity is basically the same thing as the normal force that you have. So from action and reaction forces, so it looks like the vertical components of the forces just cancel. They're equal to each other. Nothing else is happening. So oftentimes what we will do is we won't even draw them. Okay, but I'll leave them for here. So if this is my only force, well, then this is what it means. It means that my net force, so this is from Newton's third law, is equal to the summation of all of the forces. So my y forces have canceled, the force of gravity and the normal force, but my forces in the x, or in the horizontal direction, I have that applied force, right, that I have, which is equal to 105 newtons to the right, and this is equal to, by Newton's third law, mass multiplied by the acceleration. Now, if I'm going to substitute, so I know this is 105, I know that my mass is 21 kilograms, so I can find out exactly what my acceleration is. So that acceleration is going to be in the same direction. So acceleration is still a vector, so we can certainly put that in here. Now, we can solve for A, right? So my A is going to be 105 divided by 21, and I guess that equals to, 5 meters per second squared, and you can round to whatever it is that you like. Okay, I'll just keep it with 1 decimal place in here, and it is indeed, okay, so within here, so it is a vector, so that's 5 meters per second squared to the right. Okay, so we would be able to put that, and now that would solve for our acceleration as a whole. So that means that all of these, this object, this object and this object, all of these guys are moving in the same direction at the same acceleration. So all of them have an acceleration of 5 meters per second squared. This is check mark here, right? They're all moving at that particular acceleration, if that is the applied force, okay? At least for that point in time. So now what else would we want to be able to know? Well, what if somebody comes along and says, well, what is maybe the force of tension? And, let's maybe say in the rope, in the A rope. So I'm going to put a little A in there as well. So force of the tension, okay, in the rope A. So how would we do that? Well, you would have to do a free body diagram on this. So what do we know? So I'm going to kind of take this, right? Okay, I'm going to copy it. And that's all that I'm going to concentrate on. So here's my free body diagram. So this is what I know is happening in here. Now, this force of tension, right, that I have, has to be somehow pulling that cart along because it is moving at an acceleration of this. Now, it has this particular mass. So this is the only force that I have. Again, your vertical forces, right, are canceled. So force of gravity and the normal force cancel off. So I have just this one, and then there's no friction. If they had friction, we can add it, but they don't have it here, or at least this is what I stated. So because of that, we know that this is just simply equal to the net force. So there's really just that one particular force that we have in this free body diagram as a whole, right? So if we have this, then we know that this is just mass times acceleration. Well, I know my mass, which is 3 kilograms. I know my acceleration, which is 5 meters per second squared. So I know that this is going to be 50 newtons. That's going to be the actual tension which is applied in that particular kind of rope or connection, okay, in between those objects. So that's how you can find it. Now, what if you go along and start asking, well, what about if you wanted to find out? So if you now take this, okay, as a whole, so I'm going to take this and copy it, and somebody comes along and says, well, what is the actual tension, maybe in the B rope now? So in this case, so if we wanted to know what the tension is here, the force of tension, right? So in this one, so how would we break that down? Well, you would do it in the same way. So what you would do is you would combine this. So this would have been just one item. Okay, so now again, so back to one item. That one item is going to be of a mass of 3 kilograms plus 8 kilograms. We neglect the actual ropes or the connections in between there. So this is going to be 11 kilograms as a whole. The force of tension that you have, again, there's no friction. So this is the only force that is applied, which means that this is your net force from Newton's third law. And that, again, is just mass times acceleration. So what would you do in here? Well, that mass times acceleration, now it's 11, okay, within here. Acceleration was 5, so this looks like it's going to be, 55 newtons. So there you have it. So that actually tells you what that particular tension has to be. So notice the tension all the way in the left, because it only has to be pulling one of those objects or carts or whatever that might be, okay, is the smallest. And then the tension increases as you go along. So the more of these objects, or sometimes carts, if you're doing a locomotive type of example, the more that you have, the tension in the back is the least that you have. And then as you keep moving to the front, the tension increases because it's pulling more and more carts that you have, right? So that's kind of the idea with regards to these and how you can connect, okay, and draw out tension. These are, the simpler examples with regards to tension, and this is kind of in the field where you're, most likely maybe in grade 11 or in your introductory physics class. But it's a very useful thing to know, and you should understand how forces get passed on through tensions, through ropes, strings, wires, or anything like that. All right, so that is it. Thanks for watching. We'll see you in a future video. Bye, everybody.